The next third topic is potassium leaky channels. Leaky potassium, let's just fix that. Leaky potassium channels. These are ungated channels that exist in most of your living cells, and they are the most abundant leaky channels or ion channels that exist in your living cells. So what happens is, again, you have your DNA and they make this leaky potassium channel over here. There are other channels like leaky sodium channels. So there's potassium channel, there is a sodium channel, there are chloride channels. These are the main big players, and there are many other transporters and symporters, co-transporters, antiporters, uniporters that are carrier molecules that transport various ions and molecules across the membrane, both charged and uncharged, but we're looking at the charged ones right now. Now I want you to focus on the leaky potassium channels. These are channels that are open to potassium. They don't have any condition to stay open because they don't have any gates, so they are non-gated. Potassium can enter and leave the cell as and when it pleases. So if we look at the gradient again, potassium would leave the cell. Potassium tends to leave the cell more, making the cell negative on the inside, because potassium is 140 on the inside and only 4 on the outside. So if you have potassium more on the inside than the outside, potassium leaves, making the cell on the inside negative. So again, you could see that there are these different forces playing a role in making the cell negative, and this potassium keeps leaving, and there's this sort of a tug of war between these different ion channels. Potassium wants to leave, sodium comes in, and chloride, we'll talk about chloride later, it does what the other two channels want it to do. Just leave it at that. Focus on sodium and potassium. Potassium wants to leave, sodium wants to come in. Potassium would keep leaving until its equilibrium potential is reached, and sodium would keep entering until its equilibrium potential is reached. So there's a sort of tug of war between sodium and potassium to make the membrane potential closest to its equilibrium potential. You understand? Potassium leaves the cell, makes the cell negative, and it can keep making the cell negative up to a maximum of minus 94 millivolts. And for sodium, it can keep entering the cell until it reaches a maximum positivity of plus 61 millivolts. Now, potassium and sodium, tug of war. Who wins? Whoever has the most number of ion channels present. So your cells have mostly potassium ion channels N. So more potassium leaves than sodium enters. This creates more negativity in the cell, bringing the equilibrium potential closest to that value of potassium. And there is a formula for calculating your resting membrane potential, and that is called the Goldman-Hodgkin-Katz equation. Goldman-Hodgkin-Katz equation, which helps you to calculate the RMP. So how is it calculated? It is similar to the previous this one, formula of equilibrium potential. So your potential or RMP voltage is going to be equal to minus RT by F. There's no Z over here. Z refers to charge. But if we look at this, there are different ions. So which charge are we looking at? And by the way, we are looking at sodium and potassium and even chloride, and all of them are in the number one integer value. So it doesn't matter. Log base N. Now we take concentration of cation. Which cation? Let's say sodium. Inside by concentration of sodium outside. But here we are adding permeability of the membrane to sodium in this equation. We are multiplying sodium concentration with the permeability, because the membrane is not always freely permeable to one particular ion. How permeable is this membrane to the ion depends upon the number of ion channels there and if they are working or not. So sodium concentration and potassium concentration, potassium being a cation, so potassium in by potassium out times permeability of the membrane to potassium is taken into account. There is one more ion we just add in this equation, which is that of chloride. Chloride, because it's an anion, it will be chloride outside by chloride inside times permeability of the membrane to chloride. And this is your Goldman-Hodgkin-Katz equation. I want you to know one thing. Chloride's value really doesn't change the final number that you would get. That is to say, you can rewrite this equation as log base n times concentration of sodium inside by concentration of sodium outside times permeability into sodium plus concentration of potassium inside by concentration of potassium outside to permeability of potassium. And you would still get the same value. Why is that? Because chloride's contribution just happens to fall at the exact number where this equation would fall. Okay, it really just settles with whatever RMP, sodium and potassium, decide, and chloride says, hey, that's just what I wanted. You can think of it that way. So if you do the mathematics over here, you will get a value of around minus 86 millivolts. If you put in all the numbers, it comes to around minus 86 millivolts. But hold on, I just told you that the RMP is minus 90 millivolts. Now, if you see this equation, we are looking at the permeability of sodium, potassium, chloride, and the gradient created. But we are not adding the negativity created by the sodium-potassium ATPase pump directly. It was making an exchange over here. If you see 3 sodiums out, 2 potassiums in, contributing to around minus 5 millivolts over here that you could see. And also there are some negative charge proteins in RNA. So that contributes another minus 4. So with the proteins, negative charge, and RNA, and all those other proteins, it all comes to minus 4 millivolts. So if you add minus 86 to minus 4, you get minus 90 millivolts. And that is how you get your RMP of minus 90 millivolts. And that is the importance of RMP. Your cells, when they are not firing an action potential, would have an RMP somewhere around the resting value, meaning minus 90 millivolts. Most of them, not all of them. Now, some other important things that can influence resting membrane potential. Well, what if you change the concentration of sodium? So imagine you make more sodium outside the cell versus inside the cell. Well, that would affect more of the action potential. So we'll talk about that in the action potential topic. But what if we increase the concentration of potassium outside the cell than inside the cell? Somebody gives an injection of potassium chloride or some potassium solution. Okay, somebody ate a bunch of bananas and had a lot of orange juice, and ate a lot of meat, so the potassium levels just rose in their body and from their diet. So now imagine you have your leaky channels, potassium tends to leave, but if the potassium on the outside is more, this will not favor too much of potassium to leave. The gradient kind of opposes potassium leaving the cell a bit. So potassium doesn't leave the cell as it usually does through the leaky channels. It starts to accumulate in the cell, making the cell a little more positive. So when you increase potassium levels outside the cell in the ECF, you are going to cause some potassium to stay in the cell, and with its positivity, it's going to make the cell more positive on the inside, or a little more depolarized than normal. So you are shifting the RMP to a more positive value. You're bringing it closer to firing level if it's an excitable tissue, making it easy for the cell to fire more. And the opposite happens when you lower potassium level. So you have a leaky potassium channel and you have low cellular potassium level. So what happens when there's less potassium? You have a certain amount of potassium in the cell and this leaves. Potassium's leaving the cell. And because the gradient favors a lot of potassium to leave, the cell becomes even more negative than normal. So the effect of potassium value on RMP should be noted over here. It's quite important. All right. So that is the clinical aspect you can just keep an eye on with resting membrane potential. Be aware that potassium levels fluctuating can actually cause dangerous arrhythmias of the heart. And if it was sodium that was altered, that would actually cause more seizures. It's affecting the CNS more. But potassium levels, when they fluctuate, they affect the heart, the cardia more. Just remember, so your hyper and hypokalemia will affect your cardiac function. Okay, very important to remember. Can potassium level changes affect the brain function? Yeah, but it can. But you'd be dead of a heart attack before you can change the potassium enough to affect the brain. Just be aware of that also. So this is your RMP. It's a very interesting topic over here, and it's something you should not neglect. It may or may not come in the exam, but one thing's for sure, you won't be able to understand much of your action potential and other many processes like the secretion of insulin, or even the regulation of the chemical regulation of respiration via the glomus cells, because there even the potential difference across the membrane plays a role in whether these cells will work in a certain way or not, and we will go over that in those respective chapters. So that is the topic for RMP. I hope you read and get more information. There's plenty out there. Okay.